0.2. So they're very light disks, at least compared to the total binary mass. And so then we have to then wonder how much of a kind of torque can such a disk exert on the central binary and how it might we evolve them. They're also typically quite thick with aspect ratios of, say, greater than 0.3. So in Phantom, my first kind of experiment simulation suite was 16 simulations, a combination of each 4 mass ratios and 4 initial eccentricities. So eccentricities spanning the observed space from 0 to 0.6, and then mass ratios from 0.25 up to unity. All of these done with an intermediate resolution of 500,000 particles, just for the sake of time. Again, simulating relatively thicker disks, not too thick, not too thin, but aspect ratio of 0.2. And then initial periods right in the middle of that observation space of 1,000 days. The problem is generally scale-free, but I figured that was a pretty good place to start. And then simulating each binary for 1,000 binary orbits. So these very, very low resolution heat maps. Each little square corresponds to a combination of mass ratio and an initial eccentricity. And so from left to right, semi-major axis growth. I won't talk too much about this because I'll go into it in a little bit more detail later, as for reasons that might be obvious. But this is all of the binaries experience growth of about 10 to the minus 3 solar radii per year, which is not a great deal. And this is kind of what might be expected. We wouldn't expect the period to grow substantially. So that's fine. Or shrink substantially, as we might see. The eccentricity and the mass accreted from the disk, all of our simulations accrete about a third of their disk mass over the 1,000 year period, 1,000 orbits, which totals to about usually 3,000 years in total. And these rates, I've written that they are typically in agreement with observation. So the rates of about 10 to the minus 5 solar masses per year is generally on the upper end of what the observed accretion rates are. They're usually from 10 to the minus 5 to 10 to the minus 7. So this is a good place to start, at least. And the analytic predictions that I'm referencing there are from like Lion Munoz and some other disk simulations, where if you plug in the parameters that are appropriate for these kinds of systems, then these are the kinds of results you might expect. So basically, what I'm trying to say is very, very small rates of eccentricity change and very, very small rates of semi-major axis growth. Now, regarding that semi-major axis, it's always important to make sure that you do your resolution tests in Phantom and any other kind of code like this. And so I've omitted one line here, importantly, but basically this is a mass ratio of 0.25 with an initial eccentricity of 0. And again, it's important to test for mass ratio as well, because you can see these ones might tell you that, oh, it's converged, it's fine. But in reality, something strange starts happening when you increase the mass ratio to unity. And then when you include, so sorry, for context, the red line is 50,000 particles. Black line is the fiducial 500,000. And then when we bump it up by another factor of 10 to 5 million, you see that they completely, they very much so have a very big sign change, which is interesting, scared the shit out of me when I first saw it. So if anyone's really good with disks, I actually forgot to mention that I would love to talk to you about disks, because I am very much in my infancy with this. But when we look at what's actually going on here, you see that with very high resolution, in both cases, we don't resolve circumstellar disks fully, even though we know that they are present in these observations. But basically, the material has more of an opportunity to circularize. It's accreted less ballistically. And so in doing so, the torque on the binary ends up being negative. And so you decrease your binary separation instead of increasing. And this might seem like, oh, this is extremely resolution dependent, and it is. But the takeaway kind of thing is that I'm not concerned with whether or not the binary grows or shrinks. What I'm more concerned with is the magnitude of the change. And so the magnitude of the change is still quite small. So that's fine. In other words, we're not expecting a huge change in the period regardless of the resolution. So simulations suite number 2 with the electric boogaloo. At this point, I was a bit not surprised, but seeing as though we were seemingly unable to move these objects through this P versus E space, so suggesting that it is in fact a birth plot. Things have to be born with those parameters. But then I started asking, okay, how could you induce a bigger change? And the interaction between the binary and the circumbinary disk is always mediated kind of between the competition between resonant torques through outer Lindblad resonances and so on and so forth, and viscous accretion torques. And so the two ways I kind of played with that then is, well, if we shrink the disk's aspect ratio down to be a bit thinner, so that we have maybe more allowance of resonant torques to play a bit more of a role, versus then if we boost the accretion by, say, for instance, shrinking the inner the initial inner radius of the disk, so it has less time to viscously relax into its tidal truncation radius. It starts accreting right away. Then that will boost the accretion, kind of biasing the viscous accretion torques. So that's the kind of two ways I was experimenting with, just how might we induce a change. And some preliminary results from doing that. You can see the top row and this row here are thicker disks, and the second row and the last row are the thinner disks. And the most kind of important things that I was seeing was that thinner disks are much more capable of staying centrally dense for longer. They go on to go less viscous spreading. You see the density is much higher around the center. And then on here, when we plot, so the top plot, so this is initial eccentricity of 0, and initial eccentricity of 0.6. The green lines are thinner disks, black lines are thick disks. Boosting that accretion does induce a bigger change at earlier times, certainly. And green lines, the thinner disks, in terms of if you wanted to move your eccentricity, typically show, okay, maybe this might be the way to go. Unfortunately, the change is still 10 to the minus 2, so very, very small. So we're still not seeing like, okay, you're going to move your binary from 0 to 0.6 anytime soon. Not that we should necessarily expect that anyway. So I can't not use this slide. I changed this, so one ring to change them all, one ring to excite them, one ring to pump them all, and into the log. P versus E diagram, move them. So the idea was, okay, this more centrally dense disks seem to play a slightly more impactful role when it comes to evolving these binaries through this space. So what if I just went very extreme then and shrunk the outer radius of the disk down to 4 times the orbital separation instead of, say, 10? So you end up with less of a disk and more of a ring. And so these colored boxes line up to these kinds of time steps. And you can see again, the eccentricity here goes from 0 up to 0.2. And now I don't necessarily think this is all physical by any means, but it's interesting that this all happens at very early times before the disk undergoes spreading due to the strength of the interaction. So again, we still have these very large local overdensities, but even those begin to slow the rate of the eccentricity, the growth in the eccentricity. So the largest change we see happens in the first 10 to 100 binary orbits when the disk is most centrally dense. I think I was supposed to finish at 11:30, so that sounds good. So again, preliminary results. I'd love to talk to people about disks and see what I could improve or do more or do differently. But for now, I'll conclude with, never mind, I've got one more slide. So again, when we're considering whether or not things will move through this space, it seems the mass of the disk and how massive it can stay local to the binary is extremely important to the growth through the space. And then we might think, well, a ring is very unphysical and may not occur in reality. But as Kayla mentioned, after her simulations and some of the work I've done, we do have a very large mass reservoir following a kind of lighter common envelope. And so this might be exactly the kind of environment where you might see at least a little bit of growth through this space. So the conclusion of whether or not this is a birth plot, it's looking like it, but there is potential, I think, through some other parameters. And so all this to say, if you wanted it to evolve, then you should have put a ring on. Are there any questions?
That fits. Questions for Jack? I was too excited launching the poetry competition.
So APR application.
Yeah, it's the obvious discussion again.
I'm talking next, so.
It's so great.
Yeah, it was a good segment. I won't say, do you want to?
No, you kind of feel like,
Have you tried using APR?
I haven't, but I did talk to Rebecca and she did mention that circumbinary disks were the worst application because
it's still an application.
And
Worst application?
that's what, your words, not mine.
So let's be really clear. Like for APR, your whole goal is to try and speed up your calculation, right?
And you don't speed it up.
You do, but it's just you get the worst return basically.
Yes.
So the problem with circumbinary disks, in particular, like the region that you're trying to resolve, that's where you have all the tight orbits. So if you're using APR, you're then just putting more particles on the tight orbits. You still save on like the total cost. It's the lowest return for what you're doing. So I would say it's still an application, and I'm going to talk about somebody using it for circumbinary disks anyway. So I mean, it's still something worth considering.
And yeah, I was considering it. I just was beginning to then wonder what, because I would definitely resolve like circumstellar disks.
Yeah.
A lot better. But then I was wondering what is the importance of that in terms of like, would I just see more growth? And I'm not seeing as much growth as I am at the moment. So like, it doesn't really fundamentally change the outcome of the really.
That's okay.
Yeah. So.
Well, let's segue. Beck, do you want to set up? We can take another question while Beck's setting up. Quick one. Go ahead.
Hello, thank you for your talk. I wanted to ask regarding the thick and thin disk setups. This is how you initialize as a thin or a thin disk, or is evolved later, let's say through cooling, is puffed up, or?
You know, they're initialized as with a certain aspect ratio and the justification for each one.
Does it change? Let's say you have a ratio of a height and then you have, let's say, a adiabatic or cooling. Does this will make it thicker or its effect through?
It doesn't change substantially. No, I think we use a locally isothermal equation of state, and the aspect ratio doesn't change significantly over the course of the simulation.
So the temperature is prescribed as a function of radius, or
yes, yeah,
by stars in that case, if you're using fouls.
yes.
Yes. Thanks, Beck.
Thank you.